Hello, we're going to continue our lecture with section 6.4, equations with multiple angle measures. So this is pretty much 6.3 continued. Now what we're going to add to this is maybe instead of doing arg for argument, we might be able to do something else. Maybe some type of trig identity. So introduction. There is more than one way to solve an equation. For example, cosine of 2x equals 1/2. On the solving of interval from 0 less than x less than 2 pi, we can use one of the double angle identities for cosine, either 2 cosine squared x minus 1 or cosine 2x is equal to 1 minus 2 sine squared x. We can use a technique of altered arguments in section 6.3. So we can use one of these two. It just depends. We'll see several examples throughout the section, and it mainly depends on what you're given, what will be best. Let's go ahead and do example 1. Let's go ahead and solve for x when we have cosine of 2x equals to 1/2. All right, so we see that our argument is not in terms of x, it's 2x. But because we have 2x, we also have seen that as an identity. We have our double angle identities from chapter 5. So alternatively, instead of doing arg, we can also go ahead and do an identity. So we can change cosine of 2x to 2 cosine squared x minus 1. And then we see that we can solve cosine that way by getting cosine of x by itself by subtracting 1, adding 1, and dividing by 2 to get cosine squared by itself. Lastly, we take the square root of both sides, and we do that. Do not forget to do plus or minus, serving as what's cosine of x when it's equal to a negative square root of 3 over 2 and a positive square root of 3 over 2. And our answers are listed there and there. So altogether, our answers would be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now we can also do this same problem. So notice altered arguments, cosine of 2x plus 1, 2x equal to 1/2, cosine of 2x equal to 1/2. So let's do the same problem. So here we did an identity. And here we'll do altered arguments, where we set this to be arg for argument, and we alter our interval. So our interval will now be from 0 to 2 pi. And for arg, we get the answers of, we get 1/2 in pi over 3, 5 pi over 3, 7 pi over 3, and 11 pi over 3. Then we divide our answers by 2, or multiply it by 1/2. So we can get x by itself, and so our answers are the same as above. Of the two techniques presented here, we focus our attention on the second, the altered arguments technique. We do so for 2 reasons. One, the argument might have a coefficient other than 2, right? So if we look at our double angle identities, we have that argument of 2 theta, or 2x, or 2 something. But that's not always the case. We can have 3, 4, 5, a half, over 3, it can vary. And 2, even with the coefficient is 2, solving a double angle identity might not be fruitful. For example, cosine of 2x equals square root 2 over 2 cannot be solved using a double angle identity. The reason for that is once we replace it and work it out, our argument is no longer going to be, not argument, but value will be different once we change from cosine. So ideally you want to use the arg, but you can also keep in mind everything you learned from chapter 5. Let's go ahead and do example 3. Solve for theta when 0 is less than or equal to theta less than 360 for sine of 2 theta equal to 1/2. So we see that our argument is not by itself, it has something else. All right, let's begin by altering our interval. So we see that it has theta and we want 2 theta. So we need to multiply by 2. All right, so it's going to go to 0 to 720, which we know that's 2 revolutions. All right, so let's think. Let's replace sine with arg, which we have here. And I want to think, when is sine 1/2? Well, I take a look at unit circles. Sine is your y. When is sine positive 1/2? So all students take calculus. Positive is in quadrants 1 and 2. And so we see we have 30 and 150. Now to get the rest, to get that same position, you're just going to add 360. So 150 plus 360 gives us 510. And 30 plus 360 gives us that other one, 390. And if we try to add another 360, it'll be past that 270. So that's when we know we have all of our answers. Once we have our answers, we're going to change arg to what's actually our argument, to theta. We want to get theta by itself, so you know we have to divide by 2 to get theta by itself. But because we have fractions, and fractions and division can be more work, it is the same thing as saying times 1/2. So we multiply everything by 1/2, or divided by 2. So our final answer are theta are equal to 15, 75, 185, and 255. All right, cosine. We have here an argument where it's not 2 theta or 2 something. Here is where you're forced to use that argument. So here we have cosine of 1/2 x equals negative square root 2 over 2. We have to change our interval so that x matches here, right? We have 1/2 x. So let's go ahead and multiply it by 1/2 or divide by 2. Has the same effect. And so our new adjusted interval is from 0 to pi. So if you have your unit circle, that just means quadrants 1 and 2. All right, let's change 1/2 to arg. So now we're looking at this. When is cosine negative square root 2 over 2? And that only happens a negative in quadrants 1 and 2. It only happens once. If we take a look at unit circle, cosine is negative square root 2 over 2 at 135 degrees, which is 5 pi over 4. All right, let's change our argument to the value, which is 1/2. So I have arg is equal to 5 pi over 4. Let's change the arg to 1/2 x. Let's multiply by 2 to get x by itself. And we're left with x is equal to 3 pi over 2. That would be your answer. All right, go ahead and try in class example 6. So pause the video, and once you're done, unpause it so we can work it out. All right, let's go ahead and solve for tangent. Solve for x when 0 is less than or equal to x less than 2 pi for tangent of 3x is equal to 1. All right, we have to change our interval. So our new interval for x, we have a 3x, so I know I have to multiply by a 3. So let's multiply all 3 sides by 3. 0 times 3 is 0, less than or equal to 3x less than 6 pi. So 2 more revolutions. We have a total of 3 revolutions. And I'm going to change this to arg. So I have tangent of arg is equal to 1. So when is tangent 1? You can take a look at unit circle you can see that tangent is 1 in 45 degrees in quadrant 1, and it repeats again in quadrant 3. All students T for tangent, take calculus. So it happens again at 225 degrees. Okay, but we're working with radians, so let's switch that. So this 45 degrees would be the same as pi over 4. 225 degrees would be the same as 5 pi over 4. All right, so we have our arg is equal to pi over 4 and 5 pi over 4. But we said that we wanted to go all the way up to 3 revolutions, right? So let's go ahead and add 2 pi to that. Now, since we have a denominator of 4, 2 pi would be the same thing as saying 8 pi over 4, right? So let's add 8 pi over 4. So we have 9 pi over 4, 5 pi plus 9 pi, 14 pi over 4, and then another revolution more. So we add another 2 pi to that. So 9 pi plus 8 pi, we get 17 pi over 4. And then to 14 pi, we add 8 pi, which gives us 22 pi over 4. I think I added wrong, right? For the first one, 5 pi plus 8 pi is 13 pi. So this will be 21 pi. Okay. Now, let me erase that so it looks clear. So that'd be 21, and this will be a 3. All right, let's change our arg to the value. So instead of arg, we have 3x. 3x is equal to pi over 4, 5 pi over 4, 9 pi over 4, 13 pi over 4, 17 pi over 4, and 21 pi over 4. And I want x by itself, so I have to divide by 3. But alternatively, since I have fractions, I can multiply by 1/3. So I multiply all of them by 1/3. All right, let's see. Let's go ahead and see what our answer should be. So we have x, that cancels off. We have x is equal to, we multiply across. So we have pi over 12, 5 pi over 12. Here it simplifies to be 3 over 1. So we have 3 pi over 4, 13 pi over 12, 17 pi over 12. And here it simplifies as well. So I have 7 pi over 12. And those are our answers. Let's take a look at in-class example 6. So same idea. I want to change my interval to match my argument. So I have a times 1/2. So I want to multiply it by a half or divide by 2. So times 1/2, times 1/2, times 1/2, or divided by 2. Same effect. So our new interval will be 0 is less than or equal to 1/2 theta less than 360 divided by 2, 180. I'm going to put a star next to it because it's going to be important. All right, let's go ahead and change our argument to arg. So we have cosecant squared of arg is equal to 2. All right, we want cosecant by itself, so we take the square root, plus or minus. So I have cosecant of arg is equal to plus or minus square root of 2. All right, well, when is cosecant square root of 2? It's square root of 2 at 45 degrees. And we want negative and positive. So we have 45 degrees at 135, 225, and 315. Let's look at our interval. We only want to go from 0 to 180. So the only answers I want to consider are the ones that go to 180, right? So 135 and 45. So we have arg is equal to 45 and 135. Let's go ahead and replace arg with our actual argument, which is 1/2. Theta is equal to 45, 135. To get rid of that fraction, let's multiply by 2 times 2 times 2. So we have theta is equal to 45 divided by 2, 22.5, or times 2. We get 90. 90 and 135 times 2, we get 270. All right, let's go ahead and continue with our notes. So unlimited solutions. We've seen this in section 6.2 and 6.3, where we can have unlimited solutions, and if we do, we have to add a plus 1 revolution times k. And why I say 1 revolution instead of the value is because it may vary from radians to degrees. So if it's in degrees, we would add 360. If it's in radians, we would add 2 pi. And we write a k next to those values. Let's continue with unlimited solutions. So just so the words that came out of my mouth made sense. And so we write a plus 2 pi k and 360 k. Now that 2 pi and that 360 are going to vary according to our argument. If we have no solving interval, then there are infinite number of solutions represented by adding either 2 pi k or 360k. With multiple angles, we add these values before we solve for theta or x. One key difference from early examples is there is no solving interval that needs adjusting. You can just find initial solutions by making just one revolution around the unit circle. Example 7. Find all degree solutions of cosine 3 theta equal to square root 3 over 2, negative square root 3 over 2. All right, so we want to replace square root 3 theta with arg. And then we think, when is cosine negative square root 3 over 2? And it kind of helps us out. We have the answer here. We have 150 and 210. Okay, but that's our answer with arg. Now, I don't have an interval to work with, right? So that's going to affect my plus something. So I have arg is equal to 150. Arg was replacing that 3 theta. Okay, 1 theta by itself. So we have to divide it by 3, but we have to divide 3 to all 2 things. So we get theta is 50 plus 120k. And same thing for our other answer, that 210. Arg is equal to 210. We replace arg with our argument, which is 3 theta. And then we divide by 3, even to the 360k. So that's our answer. And our answer, we have to write it together. And remember to add that k contained in z. Remember that interval is all whole numbers, including positives, negatives, and 0. That's what an integer is. So it's saying along that position, I can continue moving along the unit circle and get all of my answers. I want all of the answers, all infinity answers. And here is a little chart to show you what values it could be if we plug in a number for k, or substitute a value in for k. Example 8, find all radiant solutions. All right, all radiant solutions, we have that plus 2 pi k. And just like before, that 2 pi is going to vary. It's not going to be plus 2k every time. Why is it not going to be plus 2 pi? Because we have an argument we need to consider. So let's write arg. So let's go ahead and solve for tangent squared of 2x equals 3. I'm sorry, 4x equals 3. Let's replace 4x with arg. So we're here. Now let's go ahead and take the square root to get rid of that square. Whenever you take the square root, remember plus or minus. So I have arg is equal to plus or minus square root of 3. Now when you think of your graph for tangent, has a period of pi. So we're only going to go to pi. We're going to stop at pi. 2 pi sounds misleading. We're going to stop at pi. So we only want the answers from 0 to pi. So our only answers that would work would be pi over 3 and 2 pi over 3. All right, so let's go ahead and solve it out. So when is tangent square root of 3? We get that tangent is square root of 3 at pi over 3. And we want to replace arg with our actual argument, which is 4 pi. So then we need to divide by 2. I'm sorry, by 4. Once we divide by 4, we divide to each one. Or multiply by 1/4 and get your answers. Now notice we don't have 2 pi anymore. We have pi over 4. And this is how you write them together. Remember to write that k plus z. All right, let's go ahead and take a look at this example. Actually, I want to skip this example. I skipped it in our Zoom lecture. I want to go to these. So this is an example where we can use our identities, and our only way to go about it is by using our identities. So if we for a moment ignore that we have that argument, so if I ignore this, what number that is, or what value that may be, doesn't that sine cosine plus cosine sine look familiar? If I ignore this, doesn't that look familiar? It looks like our chapter 5, our sum to product identities. No, no. My cat was drinking my soda. All right. So let's go ahead and erase them and consider them. So let's go ahead and recall. So we have a plus and I have sine cosine. When I have a combination of cosine and sine and a plus, this looks like sine of a plus b sine of a plus b, which is sine of a times cosine of b plus cosine of a sine of b. Right? And what I'm trying to highlight is that this is like this, with the exception of Instead of a, we have 2x, and instead of b, we have x. So I can go ahead and replace it with sine of a. Instead of a, I have 2x, plus b. Instead of b, I have x. And all of that is equal to -1. Well, that's a much easier task to deal with. I can go ahead and add 2x and x. So I have sine, lost my page. So I have sine of 2x plus x, which is 3x, is equal to -1. I can do the whole arg deal. So I have sine of arg is equal to -1. When is sine -1? Sine is only -1 at 270 degrees, but it wants radians, so I know that's 3 pi over 2. So arg is equal to 3 pi over 2. And I'll need to consider what my answer would be because it wants all the answers. All right. So let's replace my arg. Let's replace my arg with our actual argument, which is 3x. So I have 3x is equal to 3 pi over 2. I'm laughing because my cats are all over my iPad and my pen, and it's making it really difficult to work. I'm sorry. All right, I want to get x by itself. Because I have this fraction here, instead of doing divided by 3, I'm going to do times 1/3. Times 1/3, that's gone. Times 1/3. And we see these 3's cancel. So we're left with x is equal to pi over 2. Ew, and I messed up already. Not entirely. Because we want all answers, I should add plus 2 pi k. And that 2 pi k needs to also be multiplied by 1/3. So I would add plus 2 pi over 3k. And that would be our answer. When k is contained in your integers. Okay, let's go ahead and continue. So in class example 11, find a way to create a double angle identity. Gives you a hint to simplify the equation, and here it gives us an interval between 0 and 2 pi. Okay, I have sine and cosine. And if you recall from your chapter 5, your double angle identity, do I have a double angle identity that has sine and cosine? Yes, we do. Recall that sine of 2a is the same thing as 2 sine of a cosine of a. So it looks similar, right? I see that I have cosine and cosine, but I'm missing that 2. I don't want to change the value of my problem, right? If I add a 2, that's a totally different problem. But I know that if I multiply by 1, multiplying by 1 changes nothing. It's just itself. So when I multiply it by a special one, that special one would be 1/2 times 2. Because isn't 1/2 times 2 1? Yeah, right? Okay, so we're going to take our problem here and we're going to rewrite it. So that I have 1/2 times 2 sine of x cosine of x is equal to -1/4. All right. Now we're going to do is we're going to focus only on a very special part. For our equation, we want 2 sine of a cosine of a. So I want 2 sine of x cosine of x. I want to focus on that only. And if I focus on that only, isn't that equal to, that's equal to 2 sine, to sine 2a. So let's go ahead and replace this with 2 sine of a. But don't forget to bring down that 1/2. All right, is equal to negative 1/4. Okay, now we managed to get rid of that cosine and only have it in terms of sine. Oh, and I forgot that too. 2a. 2a. There's no 2 in front of the sine. It's just sine of 2a. Sine of 2a, sine of 2a. And you brought down the half. All right, I want to get sine of 2a by itself, so let's go ahead and times 2 to get rid of this, times 2 to both sides. So we have sine of 2a is equal to negative 1/2. Let's do the arg thing. Arg, sine of arg is equal to negative 1/2. When is sine negative 1/2? It happens in quadrants 3 and 4. It happens at, we want radians, not degrees. It happens at 7 pi over 6 and 11 pi over 6. All right, well, our argument is 2a. So let's replace it with a 2a is equal to 7 pi over 6. And 2a is equal to 7 pi over 6. And let's add, because we want all solutions, let's add that extra part. Let's add that 2 pi k plus 2 pi k. Let's go ahead and get a by itself by dividing by 2 or multiplying by 1/2. So times 1/2, that's gone. Times 1/2 times 1/2. Dividing by 2 or times 1/2 times 1/2 times 1/2. So we're left with a is equal to 7 pi over 12 plus pi k. And I wrote 7 pi over 6. One of them should have been 11 pi over 6. And now we have 11 pi over 6 plus pi k. That's your answer, and you must say that k is within your integers. There we go. And during our lecture, which went horribly wrong, I asked you to try 2 problems. I asked you to try 3 and 11. So go ahead and pause the video and try 3 and 11. All right, moving forward. For 3, this was our answer. We go ahead and replace 2 sine with arg. We find our answers, but our interval we adjusted to be 4 pi, so 2 revolutions. And we have those answers for x. For 11, it was just like our last example we did in class. We see that it looks like one of those double angles. So I have cosine, cosine, and a plus. This looks a lot like cosine of a minus b is equal to cosine of a times cosine of b plus sine of a sine of b. And you can go ahead and think of a as 5x and b as x. You can go from there. All right, thanks. I've tried to keep it as short as possible because I know some of you sat through it even though there was no audio. I apologize for that. I'll go ahead and post office hours for tomorrow. and I'll make an announcement about it. If you have any questions, feel free to post on our questions discussion board. And that's it for today. Have a nice day.